Okay, welcome. So today is a lecture that we're going to cover something that is interesting to cover because of some bad press, and I'm not hiding anything up my sleeve. So we'll see how we'll talk about nuclear energy just to give you some background and some of the particulars, and then we'll talk about some of the things, the negative things that have happened in the past year or so with nuclear plants, because 2-3 years ago nuclear was looking really promising. Less promising in the US right now, but I'm convinced that it will come around. We just have to come up with a better design that will sort of appease a lot of different people. And I think a lot of people have to understand that, you know, we have to come up with alternatives to fossil fuel. So do we use solar or wind? We're going to learn, or we have learned a little bit hopefully, about how those technologies are not dispatchable, meaning you don't know or you're not certain if the power is going to be available. So you have to step back with solar and wind and say, what's a technology that is dispatchable? Fuel cells, right, because there's a fuel source. And solar thermal, you'll learn a little bit about that because, again, there's a source of energy. And nuclear is definitely a source of energy. So anything where you actually have a source contained is a dispatchable resource. So we'll talk about nuclear today. So it is not technically a renewable energy, but as you remember from the first or second lecture, it is an alternative to fossil fuels, so it falls under the guidelines of alternative. We'll look at how you build or lay out a nuclear plant. I've been to a few of them, so I can give you some specifics there. Where we get the energy, and this is not intended to be a nuclear physics course to really truly understand a lot of the detail about how you extract nuclear energy, like if you wanted to build a nuclear bomb. I'm not the person who can tell you how to do that, and I probably wouldn't even if I did. So I probably legally couldn't. But anyway, we'll talk a little bit about how we get energy out. We'll look at some of the current technology, at least in the US, and some of the stuff that's happening in Asia. We'll look at what proposed designs are coming. There is some work to support that. We'll look at some of the regulatory and permitting issues, and this is one that really is what's killing a lot of nuclear plants, at least in the US. We do not have a good system, I think, in terms of setting up and how to get these facilities licensed. So you're seeing some issues. And then, you know, the 1,000-pound gorilla in the room is, what do we do with the waste? It exists. It's a problem. It lasts for a very long time. And what does the future hold? So we talked a little bit about it. Nuclear energy is dispatchable. It has a fuel source. It has a known supply. I'm sorry, it has an ability to supply energy, and that means that I can support some of the load. If I don't know the supply and I don't know the load, that's a very tough equation to solve. But knowing how much nuclear energy I have available and estimating what the load will be, I can pretty closely come up with and match what I have. If it's not dispatchable, say I have tons of wind and tons of solar and tons of geothermal, then I need massive amounts of what's called spinning reserve. So the concept of spinning reserve is it's operational and it has the ability to put out more power very quickly, but it's not being used. So spinning reserve means it's not outputting anything, it's just sitting there ready to go. The problem with spinning reserve is it's inefficient, right? Because if you have something that's rotating, for example, and you're not using it to its full capacity, you have losses associated with it. Right now, if it's a non-dispatchable resource, wind and solar, or PV I should say, most people will tell you I do not want more than 20% of my generation coming from those non-dispatchable resources, because it becomes cost prohibitive, and if I lose a good percentage, say, you know, I get a bad storm or something that really covers up most of my PV, or if the wind dies down very quickly for whatever reason, then I can actually have some customers losing energy. So why is it alternative fossil fuel? It's dispatchable, very stable generation. It emits no CO2. Why do you not emit CO2? You are not burning anything. Nothing is on fire, quote unquote. That doesn't mean the concept of burning the fuel or using up the fuel doesn't apply, but there is no burn. So if you see a stack on a nuclear power plant Well, most of the time when you see a picture of a nuclear power plant, it's not the actual reactor, and we'll see that in a minute. But the stack is generally closed, and the only thing it produces, every once in a while it vents out some radiation, because if radiation gets too high inside containment, then they have to release some of it a little bit. And interestingly enough, if you think there's so much radiation from a nuclear plant, there's actually less radiation produced by a nuclear plant than a coal plant. Because of that burning process, you get some unstable isotopes in the coal, in the exhaust from the coal, and you get more radiation there. Yes, sir? So the question is, how do small countries run on solar or wind if it's less than 20% of the load? And the answer is, power's there or it's not. So if you go to developing countries, like if you're at a hospital, sometimes the lights are on in the operating room, sometimes they're not. So if those are small European countries, they would have so much overcapacity for wind, for example, in Denmark. They would have so much overcapacity, let's say 40 to 50 to 100% capacity. So even if you lose half your generation, they still have twice what they actually need. They have significant amounts of spinning reserve. So they're able to make do with what they've got. Okay? So yes, that would be a case where if it's a developing country, like someplace in Afghanistan, for example, or someplace in Africa, then those are, the power is on or it's not on. And it just depends on the sun or the wind, and you just accept it. And you'll see some of the operating rooms. I read an article this past summer that talked about how there was a doctor who was trying to do surgeries, and he said, and they were asking, what would you like for donations, for gifts? He said, I'd like a backup generator. So when I'm doing operating, I can see the ventilators are working, the machines that I need are still operating, so that I don't lose power, so you can have a much better effect. In Denmark, just put tons and tons of wind. The other thing about Denmark too is they have some offshore wind, and offshore wind doesn't have a fuel, but offshore wind tends to be way more stable than onshore wind, right? It's slippery, you almost always have a breeze, so it's a slightly different configuration. Here is the production of CO2. So look at coal, this is grams of CO2 per kilowatt hour. And there's two things. This is emissions from burning is sort of the dark gray, and just the box is the indirect. So that's from building the plant, right? You have concrete that you had to produce. You have equipment inside that you have to do all these things. So those are the indirect costs. You can look at coal. It varies significantly between, up around 1,300 grams to around 900 grams. Gas, still pretty high because you're burning something. Look at the technologies that don't burn anything. Hydro, solar, this should be PV, I don't know why it's PY. Wind and nuclear. Where does it come from? Well, concrete, the curing of the concrete, the production of the concrete means you're emitting some stuff. Also, why is solar so high? It takes a tremendous amount of energy to convert sand, essentially, into PV arrays. So that energy has to come from someplace, which means you've got lots of CO2 production there. Nuclear, and this is where we see it so low, we're cheating a little bit because nuclear plants are so massive, right? 1,000 megawatts is not a big nuclear power plant. You've got a fairly sizable power plant, but in terms of its production capability of 1,000 megawatts, it's really not that large. So you can see it's pretty much the lowest of all of them in terms of CO2 production. Even less than what we would consider CO2 neutral technologies, right? Solar, wind, hydro, no burning of anything. We've already gone through this, so if we're trying to make the grid as efficient as possible and use every ounce of energy that we have, look at our nuclear power plants. If you rate it for 1,000 megawatts, it's running at 900 megawatts on average throughout the entire year. Very, very high capacity factors and very, very low differences in ranges. So that's a good thing from the perspective of these plants stay up and running when they're asked to run. And they provide really good baseload plants, because whether you go from 10% nuclear power to 100% nuclear power, there isn't much of a change in terms of the costs associated with the plant. The fuel is the fuel. You don't have a big change. The downside of having such a high capacity factor is, remember we looked at our load profiles, how they went up and down during the day and in the evening? Well, you can't really do that with the current generation of nuclear power plants. They don't ramp up and down in power very effectively. That does not mean they can't. Think of an aircraft carrier or a submarine. There are times when, let's go, we got to get out of here quickly, or sometimes they're just puttering around. They don't need a lot of the power application. So they can have that. It's just that the generation of reactors that are predominantly installed in the US do not have that capability. Next generation reactors will, so you'll see some ability to do up and down. But that's only because of the load, not because it's cheaper to run it. And then you can compare the other ones. We won't go spend too much time on this because we've talked about that. Average generation and capacity. So you can see this is 2010, so this is a little bit. But you'll notice we have 101, and I think this is gigawatt hours. Nuclear is at 92. So 91%, very high capacity. Look at the range at natural gas. Natural gas, more expensive to run. So this is our peakers, right? This is our mid, so these are up and down. Wind, what's the problem with wind? Well, you only have 40% maximum conversion of energy, so you can't get there from here. And hydro, well, what if it's a dry summer like we've had? Maybe you've got 10 megawatts of generation, but the levels in the river are so low that you can't get the power output. So you can see not a lot of capability there. This is what it estimates for new technology, and again, it's really hard to find updated figures, so unfortunately this is a little bit dated. This is from 2011, but this is estimating excuse me, what it will cost, and we'll learn more about what a levelized cost is, but essentially it is all things even, just trying to produce power and sell it onto the grid. How much do I need to sell it in 2011 dollars per megawatt hour? You can look at the different technologies. One side is dispatchable, one is non-dispatchable, right? So no fuel source. And the dispatchable technologies, you can see I've got a line in here. This is advanced nuclear. Anything below the line is more cost effective than nuclear. Anything above the line is less cost effective. So you can see it, look at some of the technologies. Coal is a slightly lower. But depending on where the government goes, we might have to capture a lot of the carbon that is produced. So if you add carbon sequestering, which means capturing it, your costs get to be much more expensive. So combined cycle, again, the costs of fuel have come down, so those are still cost competitive. If, though, we want to start doing carbon sequestration, so CCS stands for carbon capture and sequestration, you start to see that that starts to push those values. Geothermal starts to get a little higher. Biomass, right? And we don't even have carbon sequestration shown in here because biomass is considered, again, a carbon neutral. Wind, if it's onshore, is pretty competitive, but a non-dispatchable resource. If we go offshore, you can see why there hasn't been a lot of offshore, because it's very expensive to get electricity from offshore winds. PV, pretty high, but hopefully coming down as they get better. Solar thermal is very, very high because you have the concentrating emitters. So this works well in the Southwest where you can have really large facilities. Not so well here. And then hydro, we pretty much dammed everything up. That's pretty good, so we're stuck with there. So why is a nuclear power plant having a capacity factor pushing 90%? Well, you can take a look at 10 CFR, which is what applies to the nuclear industry. The US government has authorized the Nuclear Regulatory, it's hard to tell, Commission, NRC, to allow licensees to operate their plants and to oversee their operation. So if you look on their website, they have incredible amounts of regulations for what nuclear power plants are required to do. A lot of them are really good ones, but because of so much work, you can see how getting a power plant built, keeping it up and running, takes a lot of documentation. You want to make sure it's correct. You'll also, if you can click on the website, there's a lot of lessons learned. Back when 3 Mile Island, I think it's Unit 2, maybe it's Unit 1, but TMI, when they had a core meltdown, they learned a lot. One of the things they learned is when you superheat the water, it separates the hydrogen and oxygen, right? Water is H2O. When you separate the hydrogen and oxygen, now you get hydrogen and oxygen, and depending on the level of concentration of hydrogen, hydrogen is an explosive. It's a very unstable element when it's at the wrong or right concentration. So they actually asked the president of the country at the time, Jimmy Carter, to go say it's safe to be there. They weren't actually certain that the place was not going to blow up at any point in time. So they actually added the requirement that you include hydrogen monitors inside containment just in the event of a meltdown. So they called a lot of the changes, they call them post-TMI modifications. Those were requirements from lessons learned. They also had a fire, a major fire at a nuclear plant, Browns Ferry, that almost resulted in a meltdown as well. And what they learned is, even though they have redundant safety channels, that a fire in the wrong place or the right place could potentially take your plant out of service. So they developed this thing called Appendix R, which was added to the regulations to say, we need another backup system. Not a fully redundant backup system like the primary ones, but one to take us into a hot standby condition in the event that the 2 primary safety systems were out of service. So tons and tons and tons of regulation. You can look and see all the issues that have been done, all the letters, pretty interesting stuff. And every nuclear plant has an on-site NRC inspector. Gets invited to all the meetings, well, not all, the meetings that anything that has to do with the plant, so they go and they report back to corporate and they can take the keys. When I worked in New Jersey for a while, the nuclear plant that was there that I worked at, they had done enough things that the NRC thought were not safe that they took the quote-unquote keys away from the people who owned it, meaning if you run this plant, you will go to jail. So they didn't literally take the keys. There are no keys at a nuclear plant. They just did not authorize them to start up. So here's a nuclear power plant. Can't you tell? These things are evil, aren't they? The world will end if one of those blows up, except it won't, because that's a cooling tower. That's a parabolic cooling tower. Its whole purpose is to form a funnel to bring air through. All you're going to get from here is a facial. Nice steam, misty water. That's it. There's no reactive elements in here in any way, shape, or form. But in TV land, they always try to show this big, scary thing, which they show probably the least scary thing at a nuclear power plant, which is the cooling tower. The actual bad stuff is in here. These are the containment buildings. Those big concrete buildings are where the reactors are located, and that's where the bad stuff is. I was out to a power plant in Arizona that actually had a bunch of cooling towers. Why did they have it? Because there was no body of water nearby. They had a huge aquifer underground where they could get all the water they needed, but they needed to cool the water, so they built some of these. Now, you see that they have these cooling towers that have a fan. Basically, it's just a motor to draw through. So these are passive. They don't require any fans or whatever to draw through, but they're very expensive to build and operate. So now they just use electric power and they just drive it. So if you're driving up or down through Bangor and you look over in the direction of Easy in the winter, like a really cold, cold day, you'll see big plumes of smoke. It's not smoke, it's vapor, and it's from the cooling towers. They're rejecting heat into the atmosphere, so it's slightly moist water, but the dew point is so low that it immediately turns to, it goes from steam to water almost immediately. And that's why you see a big white cloud. It's just water vapor. So, cooling tower, this is for secondary cooling systems, no radioactivity here. Reactors here. Turbine building, this is where the steam turbines and generator is located. All the auxiliaries are in here for cleaning up the water, etc. You've got some buildings over here, so there's a stack over here, so this might be for some backup generation or something like that. You obviously have a bunch of buildings located nearby to help for employees to maintain the place, and that's about it. Not too much. So this one, you can see that there's no water source nearby, so that's probably why they need so many cooling towers. When I worked at Maine Yankee, they had a pond next to the plant, and that's where they dumped the warm water. They couldn't dump it directly into the river because you'd have tropical fish and stuff growing or living there, because the water temperature would be 20 to 30 degrees higher than it should be. So you have to cool the water before you can dump it back into the stream that you took it out of, and it has to be within half a degree or a degree or something. It's a very tight tolerance so that you don't raise the water temperature too much. Here's a nuclear facility. So you've got a pressurized water reactor, and you can tell because you have this is the containment, not the containment, this is where the actual reactor is. Inside here is where the fuel rods are. That's where the actual uranium is producing heat. You have these green things, which are pressurizers that help maintain the pressure in the reactor. So this is a pressurized water reactor, which means the fuel comes into contact with water only, and it heats it up and it stays in water form. It doesn't flash to steam. It flashes to steam. It doesn't flash to steam, but it's run through these heat exchangers, which are called steam generators, and the output of those goes into your turbine areas and goes ahead and does that. All right? So that pressurized water reactor would basically be, its whole purpose in life is to maintain pressure. So they might run at 560, 570 degrees, but the pressure inside the reactor is 2,000 plus pounds. Very high pressures to make sure it doesn't flash to steam. Over here, you might be 1,000 psi so that you can flash the steam. You'll notice the crane on the top, right? Because you have heavy things, so you need a crane there to make it happen. One of the other interesting things is this dome. Why is a dome there? It clearly doesn't need to be for the crane, right? The crane doesn't go that high. So why do they have such a tall dome? Remember we talked about all those regulations and whatnot? So when you design a power plant, you have to design it for a worst case scenario, which means one of these or all of these pipes here, they break. And all the water that's in the reactor at 2,000 psi and 560 degrees comes out into the containment area. What happens when you have something that's at 2,000 psi that 500 degrees and immediately goes to essentially 0 psi? Instantly flashes to steam. What happens when you go from water to steam? It expands, right? Rapidly. So this containment structure, its whole purpose in life is to contain that worst case where all the warm, hot water is dumped into containment. That's the reason why it's sized this big. And when I was at Maine Yankee, they ran a test. They had to run it every 5 years. They'd take the reactor and actually pressurize it to about 50 psi, because that's what it was designed to go without crumbling. And they say you could actually see the reactor move 2 or 3 inches, even though it's 4 or 5 feet thick concrete down here and a foot or 2 here. It actually would grow in that type of length. So it's energy. It's basically being able to contain the energy. Some people in the past have used, like you can see here, there's some water here. That can reduce some of the energy, right? Because if you have cold water, you can see that. Some of the older facilities actually had ice with boron at the top. So if you had big blocks of ice and you kept it cool until you had an accident, well, if you get something at 550 degrees and something that's at minus 20 degrees, you can absorb a fair amount of energy with ice. So they would put it on the top, it would melt the ice, and that would absorb some of the pressure, reducing the size. That's not a lot of plants because, that's a maintenance issue. So that's the traditional design. So how do we make energy in a nuclear plant? Well, we split an atom. And if you don't remember from your chemistry class, you have protons, neutrons, and electrons, right? The electrons are spinning outside the nucleus, and the protons and neutrons are sort of centralized in the nucleus. And the idea is that there's a mass deficit. So if you could weigh the protons and electrons individually, it actually has less the nucleus has less than the addition of the protons and electrons individually. The binding energy is what holds everything together and makes up that mass deficit. So keeping it all as one atom. When you split a single atom, you release that binding energy. It's no longer necessary to keep that in place, so that energy is released. And every time you split an atom, you get 3.2 times 10 to the minus 11 joules of energy, which is not a lot, but keep in mind, that's splitting a single atom, one atom, and that's it. There's lots of atoms. This is what we do in all nuclear plants in the world. You split the atom, which means it's the fission process. They are working on fusing atoms, so the idea is to take things and then combine them, and that also creates this binding energy that we could capture. That's what the sun does. The sun is a big fusion element that produces massive amounts of energy because you're fusing gases and atoms together. But the sun operates at a pretty high temperature. And so you can do high temperature fusion. Nobody has figured out how to do cold temperature fusion. That's why it's not commercially viable. They've done tons of research, but nobody has come up with the technology to do that. So how do you split an atom? You take a neutron, which is a fairly heavy, dense particle, and you force it into the atom. And that excess energy going in splits the atom apart. And that's how you get an atom to split, by taking a neutron. And that's why it explains we use uranium. We use slightly enriched uranium, and it's U-235, which is the number of isotopes. So you have a moderator, and the moderator's purpose in life is to slow neutrons down. If they came right out of a split atom here and came out, they'd be too fast and they wouldn't be able to maintain what's called a chain reaction, which is a self-perpetuating, it just keeps it going. So the neutron actually is slowed down, which allows it to impinge upon the atom and then split it into smaller sections. Then that releases more neutrons to continue the process and to continue the process, and then we have a chain reaction. It just keeps going and going and going and going. You have control rods, which are made out of boron, and they absorb neutrons. So how do you shut a nuclear power plant down? You drop the rods. They're located within the fuel, so they're boron, and they just stop the chain reaction because they're absorbing neutrons. That does not mean that it stops at 100%. It's still radioactive, but it's not producing the power it once did before. So 235 is the only readily fissible material. You need the precise amount of uranium-235, otherwise it will not be fissible. It'll be either too many or too little, and you will not be able to maintain a chain reaction. Why do we enrich uranium? Because when you dig it out of the ground, only 0.7% of the uranium you dig out of the ground is going to have the right number of neutrons in the atom. So you enrich it by getting rid of the stuff that's not U-235 and just leaving the U-235. So you have about, usually for commercial reactors, it's about 4% enriched uranium. And that's when you use centrifuges to separate the atoms and go from there. Your chain reaction must be controlled. Like in a case of a nuclear bomb, it is somewhat of a controlled reaction where it's releasing its energy as quickly as possible. Okay, that's how you get the loud, not the loud, but the fast expansion, the heat, and whatever. You don't want that in a nuclear power plant because you want to just generate heat and capture that heat. So you have to control it. Okay? And once you keep the chain reaction going, that's called being critical. Your reactor is critical. You're actually splitting atoms and they're splitting the process. Uranium is not stable in and of itself. It always releases energy. So even if it's not been irradiated or not been forced to split, your uranium is still radioactive. And it's very low because it takes 704 million years for uranium out of the ground to release half its energy. So you can see if you have a handful of uranium, it's not releasing a lot of energy if it has to take 704 million years just to get to half. It is very dense, but not as dense as gold. So if you really want to use fancy weaponry, right? Why are bullets made out of lead? Because it's high density and a very small particle size. So if you can propel that bullet, it actually can penetrate because it has a small surface area to impinge upon with a lot of mass. Uranium is even better, and depleted uranium is what they typically use for armor piercing because it's so dense and it's readily available once you've reprocessed, or not reprocessed, but you've created some fuel. So, and it's not obviously precious as gold. So armor piercing, that's one of the things you can do with depleted uranium. It's not radioactive, it's just, it's very dense. So we enrich it to, like I said, about 4% for typical commercial reactors. Highly enriched, 85%, that's considered weapons grade. That does not mean you can make a weapon. You have to have very specific technology and to do it. So if it's highly enriched, you might use it for fuel for a submarine, or you might use it for an aircraft carrier. Why would we do highly enriched fuel? Think about the size. It's much smaller, and when you've got limited space, then you want to have it to be highly enriched. So you want it to be as small as possible. Also, you don't want to be changing the fuel out. In a nuclear power plant, they change the fuel out, well, not all of it, but a third of it every 2 years. So the fuel is good for 6 years. In a submarine or an aircraft carrier, it's not an easy process. Those are designed to last 10, 20, 30 years on a submarine, much, much longer, because to replace the fuel in a submarine, you have to cut a hole in it, essentially. And nobody wants to do that in a submarine as far as I know. Why is uranium so good? Because if you can capture that binding energy, 1 pound of highly enriched fuel is the equivalent of about 1 million gallons of gasoline. And in a can of Coke, you can put 15, so 12, less than an ounce, you got over 1 million gallons of gasoline. Right? So imagine if you buy a car with 1 ounce of uranium, you can drive it for essentially forever, right? You never have to fill up with gas. So is this something that will be the future? Who knows, right? We're talking about electrification of cars. Energy storage, right? We have lots of density. Really powerful here. So we talked a little bit about this. So it's not very radioactive. We've taken out all the good stuff that we want for the reactors, but we have to deal with the depleted uranium because we do worry about armor piercing. Here's the largest uranium mine. So it's the Olympic Dam mine. It's in Australia. It's owned by a subsidiary of BP. So I just put BP because it's actually BPH. And they do a bunch of different things. They don't just mine for uranium. They mine for gold and a bunch of different things there. But essentially, this is the largest uranium mine in the world. They do some uranium mining in the US. They talked about expanding this in 2011, but then they changed their mind based on projections for uranium. If there's not much demand, then they won't do it. So this is a consequence. This is one of the things when we talk about alternative renewable energy. Obviously, you have to dig up the ground, right? You have to do a lot of damage to those areas. But that doesn't mean coal or natural gas is any better. They have their own set of issues, right? We just don't see it because it's not in our backyard. So a little bit more about the moderator. So if we don't have that moderator to slow down the neutrons, it would not capture the energy, so we would lose it. It slows it down by absorbing the energy. So that's why in the US we use water, very clean water, to absorb that energy, which means we heat it up and spit it out and use that to heat. There are different types. There's a light water reactor, which is just very clean, may have some boron in it, but very clean, so has a very low conductivity, does not cause lots of corrosion. That's every reactor in the US is a light water reactor. Heavy water, they add deuterium, so we don't absorb the neutrons, we actually change the speed, but we're not absorbing them with the water. So it is more efficient than a light water reactor because we're not taking those neutrons that we're going to do something else with and provide those to the water. So in terms of the chain reaction, a heavy water reactor is more efficient. And you don't even need to have enriched uranium in there. It can enrich uranium. So you can take a heavy water reactor and you can get more radioactive or more enriched uranium out of it. So you can get plutonium. Okay? That's part of the process. If you go to France, they reprocess their spent fuel, so that's why they don't have as much spent fuel as we do, because they keep reusing their fuel. So they don't have to mine as much, they just keep reusing it. The problem is then you get plutonium and it gets more dangerous to deal with. You can also use graphite. Graphite is another moderator, and that's used for very, very large reactors. The problem with graphite is that once it's on fire, it is almost impossible to put it out. That's what happened with Chernobyl. They had 2,000 megawatt reactors. They were so big that you couldn't use water to moderate them. So they used graphite. And unfortunately, graphite got so hot, it caught on fire. And once it was on fire, you just couldn't put it out. So that's when they had the meltdown at Chernobyl. The other thing about Chernobyl too is they did not have a containment building. They essentially had a metal building around their reactors, and that's why when it blew up, it had tons and tons of radioactive releases. And so we talked about these already, so we won't repeat them. Here is, as of May 2017, we have 99 reactors to operate. I don't know what the decision was based on that. Maybe it's the vintage, perhaps, or maybe it's the PWR, BWR. But you can see, you know, we don't have a lot in the US anymore. I mean, on the East Coast. We only have one in New Hampshire. I think that there is only one left in Massachusetts, although that's probably going to be 0 pretty soon. In Connecticut, we have 2, and that's it. Okay? If you notice, down south, they have a fair number of them, a few in the West, and in the Midwest, we have a fair amount of them. Population centers, right? Focus where the population is. Yes, sir? So the question is, why are they getting rid of the reactor in Massachusetts? A couple reasons. Most reactors most nuclear power plants are given a 40-year operating license to start, and then you can apply for a license extension if you prove that the plant is safe to operate. So I think it's Pilgrim is the one that is going to be closing in 2019. A couple reasons why. They've got some issues with their transformer that's kind of on the edge. That'd be a very expensive purchase. The market has changed. So combined cycle power plants, you saw the levelized costs have come down a lot. So the owner of the nuclear power plant just can't make money on it anymore. So they're going to decommission the plant. Vermont closed. There's some political reasons for that. But again, it's a very competitive market. It's hard to compete against fossil fuels at this point without, again, all the sequestration stuff. So 99, that includes, no longer one in Vermont. There used to be, I think, 1 or 2 more in Massachusetts, 1 or 2 more in Connecticut, and we had 1 in Maine as well. So we've dropped quite a bit in New England. We have about 400 nuclear reactors in 31 countries, and it shows you a sense of the size. So the bigger they are. It also has a color scheme showing you whether it's been operating, if it's offline or shut down or under construction. So you can see there's a few in the US, and we'll talk about those in a little bit. A lot happening here in Asia, right? Lots of opportunities here. Still in Europe, and quite a few happening Saudi Arabia, right? Building power plants. Even in Saudi Arabia, where they have lots and lots of fossil fuels, they realize it's an opportunity to go. You'll see that there's a red dot in Maine. That's because it's shut down. It's shut down in 1996, and if you go to the site, you wouldn't even recognize there's a nuclear power plant. They still have the spent fuel there, because all the ones in the US, all the spent fuel are still at the operating facilities, because they don't know what to do with them at this point. So there's no central repository. The Department of Energy has supposed to have come up with one, but they haven't figured it out what to do. So we still do not have a place for spent fuel. Almost 11% of the electricity in the world. Quite a bit. So how do we generate electricity? In the case of a PWR, the moderator, right, which is slowing down those neutrons, that's called the primary. That's actually coming into contact with the reactor vessel and the fuel. it's at such a high pressure that even though it's at 560 or 70 degrees Fahrenheit, it does not flash to steam because it's at over 2,000 pounds pressure. Then we go to a a steam generator or a heat exchanger, and we have a primary and a secondary side. So that isolates the primary and the secondary. So there's no physical thing. There's only a pipe between the water on the secondary side does not come into water on the primary side. We drop the pressure and we flash it to steam. And the steam is not a high quality steam. It tends to be a lower quality steam with some moisture in it. You can see the temperature, 540 degrees. One generation or one type. The other type is a boiling water reactor, which is the primary, goes directly to the steam turbines. So pressurized water reactor has less equipment that is contaminated because in a BWR, right, the moderator is directly coming into contact with the steam generator. So when you go to a BWR, you have a much wider area that has to be, you have to wear radioactive sensing equipment and be mindful of what you're touching. In all cases, all it is a source of heat and steam. So whether it's coming from an engine, not an engine, but a boiler that's burning coal or wood, or if it's coming from a gas supply or something like that that creates steam, they all drive a steam turbine generator, which means a turbine driving a generator. That's how you extract it. So little ones today, 600 megawatts, big ones are 1,300 megawatts. Here's a PWR. So here's the reactor vessel with your control rods. And your control rods aren't exactly what you think. Most people think, well, if I want to increase power, I pull the control rods out. That's actually not how you do it. You pull the control rods out and then nothing happens. How you actually get the process moving is you lower the temperature of the moderator, right? That makes it more dense. Less neutrons are being slowed down. So it hits the fuel, splits the uranium, and there we take off from there. Pressurizer maintains that 2250 psig, so this is a very sensitive device to maintain pressure. We run to our heat exchanger. We run secondary system, not in contact with the primary system. Water here, steam to the top. Steam generator steam goes to our turbines. And then under here is the condenser, which is under a vacuum, right, to try to extract as much energy as possible. Now it's cool water, we pump it back to the steam generators and we do the process over again. Same thing for the primary side. We have another set of water, so in your secondary system you have water, but then you also have to cool this down a little bit. So this is circulating water. This is from the river or pond or whatever you had, and that is, you know, twice removed essentially from the primary. So generally you don't have to worry about any radioactivity there. And then you send it out to your cities. Here's a BWR, and the only difference is there is no steam generator here. Everything goes to the steam turbine. So this water here, you have to monitor it more closely, because if you have a leak in any of these tubes, you can have some radioactive material going out into the atmosphere. So all that stuff has to be monitored. But all the difference is steam is generated here and not here. So you have to be mindful about, hey, I can't have any fuel that is going to flash or be around steam because I won't be able to remove the heat, and then I can have a meltdown. So slightly different reactor design as well. We're pretty much generation 2. So first generation was back in the 50s, smaller plants. Everything since then has generation 2. So we have boron injected to help control the reaction. So once we start a plant up, we just pull the rods and we don't worry about it, we leave them up. We use a little bit of boron to increase or decrease. We have an unbelievable amount of automated control systems. I wouldn't say hundreds, but many, 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 where they're sitting there monitoring temperatures and pressures and radioactivity. And if any of those take off, well, you don't want to trip the plant. You want to make darn sure you have an issue. So a lot of times you have a voting scheme. So like you might have 4 systems monitoring pressure. And if any 2 of those systems say there's something wrong with the pressure, then it would initiate what's called safety injection. Or you may have a 1 out of 2 taken twice. So you basically have 2 channels. One channel has 2 separate monitoring devices. The other one has 2 separate monitoring devices. Either one of those, one channel has to, on either side, has to say yes, there's a problem, and then that's going to issue a trip command. So that's 1 out of 2 taken twice, or 2 out of 4. Generation 2, because you have to get rid of the heat, you must have some sort of on-site electrical power to help pump cold water through there. So that's a problem with Japan, right? The reactors there, I think, were built in the 60s. You have to have on-site emergency generators. And all they do is take the plant to what would be a cold standby. Will they do cold standby? This is hot shutdown. You can definitely do hot shutdown. I thought you can also do cold standby, but I could be wrong. And you have 2 trains, and they are 100% redundant to each other. You only need 1 train to take you to a safe condition. And these are physically isolated from each other, so that if you have a fire or an explosion, train 1 would not be impacted from the one that's on fire or one that failed to operate. So you have to have 2 generators, 2 pumps, 2 distribution systems, 2 batteries, blah, 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 on and on and on to have that reliability. So again, that's what makes higher safety, but is very expensive. We talked a little bit about the TMI Unit 2. Well, Unit 1, which is adjacent, is still operating today. So even though they had a meltdown at number 2, it is not a problem that they can't run it. We talked a little bit about the hydrogen monitoring. We also added some radiation monitoring to prevent, radiation being released in the environment. And then I talked about the Browns Ferry, had a significant fire that almost resulted in a meltdown. And they had to add another system called Appendix R, which is not as reliable, but it's only in case of a fire. So you're not figuring there's this major accident, taking out both trains in a fire, and go from there. A few of them are still being built in China to save costs. In the US, where are we looking to put new reactors? You can see there is a lot of colors there, right? Approved, proposed, but look at the date here. June 2017, this is what was proposed, maybe a dozen or so. South Carolina Electric and Gas ceased construction, right? Sumner Nuclear Power withdrew requests for Calvert Cliffs, Grand Gulf, 9 Mile Point, and all those plants. So you can see how a lot of these, like the ones here, so you can see VC Sumner, that's gone. They pulled the plug. Calvert Cliffs, which is in Maryland, so let's see, Maryland's here. I don't see that it's shown up here. Must be these 2. Stopped. Grand Gulf, not going forward. They're still talking about approving to move forward in Georgia, but we'll see why that might change a little bit as well. So Generation 3 has been around for about 20 years. It has a better fuel design, so it avoids any entrapped air, meaning it is more efficient. You optimize the use of your fuel. It is a more efficient, which means more production. Here's the other big thing. You don't need backup power to keep the plant cool. It just uses natural circulation, right, which is based on density. So a much better design, so you don't need as much power. It's more reliable inherently. It's fully digital controlled. It used to be everything was analog, so you had something turn on, and then this turned on something else and turned on that. This is all digital control. One of the projects I worked for when I lived in Washington, D.C. was getting a PLC, which was a triple redundant PLC that was used extensively for the fuel, pumping refineries and stuff like that, where it was really critical not to have a failure. It was triple redundant, so you had one input, but then it would take that input and separate it and go to 3 completely different cards, and they would vote a 2 out of 3 condition, basically. It's a pre-approved design, so you say, you log on to your account and say, I'd like to order 1 Generation 3 reactor and build it in 4 years. So it's a pre-approved design by the NRC, which makes construction much, much easier. Yes, sir? Japan, so the question is, why does Japan like nuclear power so much? That's a tough question for me to answer. I'm not from Japan. If I had to guess, most of the time the reason why you settle on nuclear power, well, a few big reasons. You don't have the resources, so you don't have a lot of coal or fossil fuel. And another big reason is environment, right? If you think about a nuclear power plant, you don't burn anything, you don't produce any CO2. So it's a very not economical, but it's very environmentally friendly when you consider the fact you're not producing any CO2. Also, Japan is a very dense country, so they do have vehicles and cars, but a lot of people get by on electric transportation, subways, trains. So as a result, it doesn't make sense to have lots of gas stations and whatnot because everybody either walks, rides their bikes, or takes the train. So my guess is that no resources, very limited resources, and it's electricity is the way of life there. They're more concerned about the environment. And I've never been to Japan, but I've heard it's very clean, environmental as well. France, I think, has even higher percentage of nuclear power. And again, resource poor, concerned about the environment. So something like 90% of their power comes from nuclear, very, very high percentage. Here's a little bit of an older picture, but this is a reactor. This is a Generation 3, this AP1000. There's two of them that was built in Sanmen, China. Okay, so standardized design makes it very efficient. Here's Westinghouse's design, or proposed design for this AP1000. They're pre-approved, and Westinghouse was pretty much the only game in town. Back in the day, there was Combustion Engineering made them. GE made them, and Westinghouse made them. There was sort of three designs, just depending on which way you went. So very similar, right? It's a pressurized water reactor. You have a slightly different containment structure, so smaller, slightly smaller. You have a passive cooling water tank, which is located at the top of containment. So as it gets hot, this water almost rains down and helps to cool it. So instead of having ice, you just have a massive amount of water at the top. You only have 2 steam generators, 4 reactor coolant pumps to circulate the primary. Your vessel is down here, hard to see, sorry about that, but everything else is the same. Just a slightly different fuel design and the addition of water at the top. So as you rain down, that's absorbing the heat, it flashes back up the steam, gets to the top, it cools down, and rinse and repeat the cycle. Next generation is Generation 4, which hopefully will be out sooner than later, because they are going to completely change the way we deal with spent fuel. So now spent fuel takes thousands and thousands of years to be no longer radioactive for the fuel. Generation 4, the design will allow the radiation to be spent in decades. So instead of having to design a repository that has to be around for 10,000 years, you might need something that will last for 30 or 40 or 50 years. You can design something to handle that. It's very difficult to design it otherwise. It'll be very efficient. Another big advantage is all that Generation 2 reactor fuel that we have located all through the country, they'll take it out, ship it out to these Generation 4 reactors, and they'll reuse that fuel. So you'll have less fuel to deal with, and it won't take millennia for it to be less radioactive. Will that change? Well, you see, depending on administration, lots of changes occur, but nobody has broached the subject. President Carter said no reprocessing in the US. That can change at a moment's notice as long as somebody approves it. The other nice thing too is you can also extract some heat to process hydrogen for fuel sources. Why would you do that? How about a hydrogen car? Right? Hydrogen is a fuel source. We can take it and actually we can use that instead of using fossil fuels. We can use hydrogen to drive our cars. And there are 6 different designs being proposed. So here's sort of the walking its way through. You can see that Generation 3 started in '96. It's going to be around for a while. Generation 4, they're hoping will be 2030, 2040 time frame when those will be ready to go, and then that will allow us to get fuel for many years. But that's unfortunately a long way to go. So what are the issues? And we got to talk a little bit about problems, right? Because everything seems great until we start talking about some problems. Well, the NRC is the one who gives you the keys or allows you to operate your plant. It is extremely intense review process because you can't have a mistake at a nuclear power plant. If you do, then lots of people may die. And it leaves the environment around there for many years in a rough situation. You can take a look at some of the stuff from Chernobyl and how they basically just closed the city overnight because of the radioactivity. It has to be a very, very good environmental situation, meaning very little earthquake issues, although you saw a bunch of them that were built in California, so you can overcome some of those. Have to be careful about tidal waves, typhoons, that type of stuff. You don't want to be something in Tornado Valley where you get 300-mile-an-hour winds. There's not much you can design to stop a 300-mile-an-hour wind for that. It takes a long time, at least 3 years, and protesters can try to shut it down. They can go to court, see if they can do a restraining order preventing you from continuing on. The NRC is trying to issue a general permit, but the NRC is allowed by the legislative body. The court is separate. So just because the NRC says, well, you can't challenge that doesn't mean the court has to agree with that. So will this ever happen? Who knows? It would be nice because that would prevent any further roadblocks. What do we do with the waste? That's another problem. Well, there's a bunch of different types of radiation: alpha, beta, gamma, and neutron. It depends upon how the body is ingested, meaning taken into your body. If it's on the outside of your body, your skin is actually a very good radiation shield for most types of radiation. Think about it. We can go out in the sun and not die immediately, right? Because our sun does a pretty effective job of preventing the radiation from coming into the sensitive parts of our body. That's why we have multiple layers of skin, and the top few layers are dead skin, protecting our body from radiation. If we get radiation inside, so if we breathe it in or we swallow something that's radioactive, we don't have that protection inside. So it can be a lot worse. What happens anytime you have energized particle that penetrates cells? They damage the cells. If the cell dies and that's it, it's fine. If it doesn't die and it mutates, that's called cancer. And then it can become very fast growing, and it can, basically what cancer is cells in your body doing things that they're not supposed to be doing. And it causes lots of pain and a bunch of different things. So yes, it's a real issue. We want to avoid cancer. So that's what most people will die if you're exposed to radiation. You have cells that create cancer. That's a long-term exposure. If you have a powerful enough dose initially, you can die very quickly because there's so many cells that have died, your body can't sustain itself. NRC gives you guidelines based on tons and tons of research. There's, eyes can get so much, skin can get so much. It just depends on that. Anything that is rapidly changing, so if you're an infant or fetus, even worse, because the cells are splitting so quickly, those are very sensitive, because if you have one cell that mutates, they're reproducing so quickly, you can very quickly have problems. So fetuses, pregnant women aren't really allowed to work at nuclear because the fetus is very sensitive to radioactive. If you work at a nuclear power plant, you work on the non-radioactive side. We have different types of waste too. We have low level and high level. Low level is contaminated stuff, so you might get a particle that has broken off from the fuel inside containment and it's radioactive, and so it's not producing a ton of energy just because it's only a few particles. It's very small. So oftentimes when you go where radioactive material is found, you have to wear clothing that doesn't protect you from the radiation, because that's not what it's intended to do. It's just intended to keep it from getting onto your skin. So when you go into containment, you wear gloves, and you wear clothing, and you wear a hat, or not a hat, but a hood, and things for your boots, and you go in there, and then when you come out, You take all those clothes off and you take them off in a specific way, and then you check to see if you have any radioactive particles on you. Hopefully you don't. Then you're fine. They take those clothes and they launder them. So they run them through, they release whatever there, they capture anything that's radioactive, and then that's treated as low-level waste. Because it's expensive to dispose of it, you compress it and compress it and compress it. You make it as small as possible, and then you put it in a landfill. You can create a dirty bomb from it, right? So if you have some low-level waste, you can handle it. The person who's handling it may still get sick, but the bigger concern is if you create a bomb and then you explode it, now you've got all this material that's contaminated spread out over a wide area, and it takes a long time to clean it up. You also need radioactive devices used in hospital for medical procedures. Lots and lots and lots of radioactive waste. Every time you go get an x-ray, right, they stick the lead blanket on you and everybody leaves the room because you're going to be bombarded with some radiation. High level waste is spent fuel. That's the dangerous stuff. Very, very strong levels of radiation and neutrons that can go through your skin. If you're exposed to high level waste, you can die very quickly because your cells will mutate and they will no longer work. Also very long half-lives. We talked about millennia, so long periods of time. So what's the answer today for radioactive waste? You put it in dry cask storage. So you take it out of the spent fuel pool, which is what most reactors have next to them. It's just a pool with water. Water is a great moderator to slow down the neutrons. So you have 20 feet of water over your fuel, and it's essentially no radiation. I've looked down at spent fuel and essentially received no radiation. So it's not radioactive at all once you get through the water. It's a good filter. Lead's really good too because lead's very dense and it's hard for neutrons to sneak through. So you have a bunch of fuel that is all mounted. So all this stuff is done underwater. Excuse me. Then you put a canister around it. Then you put concrete all around it, leaving some gaps for air, because remember, this is hot. So you allow air to go in and come out, and it's just cooling. There's no actual access for whatever's inside the spent fuel, and then you set that outside. So if you go to Maine Yankee, which is in Wiscasset, and well, where Maine Yankee used to be, you'll see, I don't know, 50 or 100 of these caskets just sitting on site waiting to be moved to a new location. Very heavy, right? Not like somebody can just pick one of these things up, but if somehow you could get through and cause an explosion, you could cause a lot of damage. So, you have to make sure that people, the bad guys, can't get too close to it. Where is it stored? Everywhere you see a nuclear power plant has been, and then some. So you see a bunch of places over here in Oregon and Washington. That's where the government did a lot of work for, creating bombs and such. So a lot of why you see more than just a few, more than the number of power plants, is primarily because where research is going on, and that's where they store the high-level waste or low-level waste. Sometimes you could take it to South Carolina and just dump it. Yucca Mountain is proposed to be the long-term storage, but it's been talked about for 40 years, researched, and still hasn't happened. So will it ever happen? I don't know the answer to that question. So what's the future? Well, with Generation 2 reactors, we got about 100 years of known uranium fuel left, and that's it. If we go with next-gen reactors, which we can reprocess fuel, we don't need to enrich the uranium, we can have thousands of years of fuel. Many, 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 many years. So running out of fuel is not an issue. We do have to worry about nuclear proliferation, which means the bad guys get a hold of the waste and do bad things with it. So how do you control that? Hospitals have issues with that too, right? Big issue. Our new designs must include being able to change power output more rapidly than they do now. We live in a deregulated market for many states in the US. How do we ramp up and down more quickly to respond to load? If you do that, you become more attractive, because fossil fuel plants can do that, no big deal. And finally, how do I mitigate the risk? And not proliferation risk, but construction risk. So back in January 2017, Siemens Westinghouse, which builds the only reactors in the US, filed for bankruptcy protection, mainly because of cost overruns with the power plants that were being built in Georgia and South Carolina. So one of the issues was they've been building plants in Japan and China and Europe for a while, so they thought they knew what they were doing, and they do, but they hadn't considered maybe how the NRC was perceiving how to do things, and how other organizations, government organizations, were doing things. So they were being slowed with construction, they were being challenged, and things that were taking, should have taken a short period of time were taking an inordinate amount of time, and more documentation had to occur. So because of the cost overruns, they had to file for bankruptcy protection. And there's discussion that actually might take down the parent company, which is Toshiba. So what does the future hold? Right now, it's not looking good, but I think it will take another event like really high oil prices, or somebody has to accept at some point that CO2 production or emissions are becoming an issue, and that changes based on the administration. So too many unknowns at this point. So if you were a betting man or woman, would you bet on it? It's a tough call. Right now, I don't know, but in 10 years, things could completely change. There has been more discussion. If you've heard about all the hurricanes that have been happening this past summer, 1, 2, 3, 4 big ones in a row, that's been leading people to talk about, well, maybe global warming is in fact an issue. Maybe it's a concern. I know it's September 26th today, and it was 90 degrees yesterday. So that's pretty odd for northern Maine or middle of Maine to hit 90 degrees in September. So maybe there'll be more scientific proof. Maybe somebody will finally prove that it's an issue and we have to do something about it. Who knows? So that's all I had for nuclear power. I think it's a very interesting field. It will come back. It is back in Asia and Europe. Will it come back to the US? Don't know. Questions? All right, if we have no questions, well, don't forget you have a test on Thursday, so we have no class on Thursday. Test should go live at 8 a.m., and you'll have almost 2 days to do it. So good luck, and I'll see you next week.